Carbonate equilibria. Carbonates are arguably the most important dissolved component of soil solutions, and in alkaline soils, this statement is even less disputable. Implicit in this statement is the relationship among dissolved carbonate species, whether or not they are in equilibrium with solid phase metal carbonates. The simplest example of carbonates is the control which dissolved carbon dioxide has on water pH and buffering. In this section of the course we will consider the effect of carbon dioxide on water pH, the influence of solid phase calcium carbonate on solution composition, and the implications of these reactions. Contents: carbon dioxide in the atmosphere, the carbonate system in aqueous solution, distribution of carbonate species in aqueous solutions, alkalinity and acidity of carbonate-containing waters, effects of biological processes on pH and alkalinity. In the last is seawater. Natural waters, which include the ocean and freshwater lakes, ponds and streams, act as a major interface between the lithosphere and the atmosphere, and also between these environmental compartments and much of the biosphere. In particular, the ocean, with its large volume, serves as both a major reservoir for a number of chemical species. The deep ocean currents also provide an efficient mechanism. Natural waters contain a variety of weak acids and bases which include the major elements present in living organisms. Carbon dioxide in the atmosphere. CO2 has probably always been present in the atmosphere in the relatively small absolute amounts now observed. Precambrian limestones, possibly formed by reactions with rock-forming silicates. The concentration of carbon dioxide in Earth's atmosphere is currently at nearly 1 parts per million ppm. The carbonate system in aqueous solution. In an open carbonate system, the aqueous solution is in chemical equilibrium with atmospheric CO2. Unlike the closed system, where the total amount of inorganic carbon DIC remains constant as the pH changes, the amount of DIC in an open system increases with increasing pH. Distribution of carbonate species in aqueous solutions. In this section we will look closely at the way in which the concentrations of the various carbonate species depend on the pH of the solution. This information is absolutely critical to the understanding of both the chemistry of natural waters and of the physiology of CO2 exchange between the air and the blood. Alkalinity and acidity of carbonate-containing waters. The concepts of alkalinity, acid neutralizing capacity, and acidity-based neutralizing capacity are extremely important in characterizing the chemical state of natural waters, which always contain carbon dioxide and carbonates. Effects of biological processes on pH and alkalinity. Most natural waters contain organisms whose activities affect, and in many cases may exert a major control over, the pH and alkalinity. Seawater. The chemistry of the oceans is a huge subject that we cannot begin to do justice to here. As can be seen in Table 9, seawater is composed mostly of a few major cations and anions that account for the bulk of its dissolved solids content. How carbonate equilibria in natural waters affect environment. First, the pH of seawater water gets lower as it becomes more acidic. Second, this process binds up carbonate ions and makes them less abundant ions that corals, oysters, mussels, and many other shelled organisms need to build shells and skeletons. And also carbonate equilibria affects atmosphere. Carbon dioxide increases temperatures, extending the growing season and increasing humidity. Both factors have led to some additional plant growth. However, warmer temperatures also stress plants